You know how nowadays when you open the YouTube app on your phone, YouTube just instantly gives you a short form video even though you didn't choose to watch that particular short form video or any short form video for that matter? To be honest, I find this feature kind of annoying because it makes me feel like a human version of a foie gras duck, where my brain is just being forcefully fed useless, contextless content that I didn't ask for. I think that there should be maybe we should try two apps, one for long form content and the other one for short form content. All that being said, yesterday, YouTube has forcefully shown me a short video that I really liked and I found really interesting. This video. And as you can see here, it says, let me read it. Before electricity reached the tropics, the Swiss solved cooling with clockwork. One full crank of this spring motor fan gave you 30 minutes of continuous breeze. No power source needed. Of course, like most short videos, this video is just a reformatting of somebody else's long video, and I did find the original video eventually. And as you can see, what we're looking at has a name. It's called a Paillard clockwork fan. It's a Swiss hand-cranked fan from the early 1900s. And again, in the original video, the statement that it does 30 minutes of cooling on just one full winding is repeated. Unfortunately, that statement is never proven, so we are forced to trust the uploader because he never shows the fan actually cooling you for 30 minutes with a stopwatch next to the fan or something, I don't know. I personally find it highly doubtful that it can do 30 minutes based on the size of the fan, and I did find another video of a similar device from a similar time that did 14 minutes. But even 14 minutes is honestly kind of impressive on just one full winding. And I thought, hey, these are ancient fans from the early 1900s. We must be able to do something much better today. So I decided to look around to research to find the modern equivalent of these manually wound fans, and I found nothing. There is no modern equivalent of this. Nobody makes this anymore. All we have are fans that are plugged into the electricity grid or powered by batteries. The only manual fans we have are either you have to constantly wind them or you have to constantly squeeze them. So you have to constantly operate them, which is honestly kind of annoying and useless, and your hands get tired after just a few minutes. So there's nothing that's the modern equivalent of this, which I find pretty surprising because there's a market for this. We're all about energy nowadays, and what's better than free energy? You always have your hands with you. You just wind it and you have free cooling. A lot of people want to live off-grid nowadays, or at least pretend to live off-grid, and electrical motors are pretty power hungry, so this would really be useful. There's a lot of people who live and or work in remote, hot areas where there's very little electrical grid coverage. This would also be really nice during a power outage. In general, it's something useful to have. So I decided to try and build one myself. And if successful, I will share the files for free with you. Obviously, the first step towards building it is understanding how it works. Fortunately, the video gives us a lot of very useful clues. So the first part here is our gear train. And all this does is that it increases our output speed. The fan is our output, and we want it to spin fast enough so that it can move a substantial amount of air quickly in order to cool us down. If we observe the mechanism while it's running, we can see that our input is this gear right here. As you can see, it rotates very slowly, and as we move up in the gear train, the gears rotate faster and faster. So we have high torque and low speed here, which we then convert to high speed and low torque here at the fan using our gear train. The next question is, what is inside here in the box underneath the gear train? Well, this is called a clockwork fan. We can see winding and hear ratcheting, and the short video mentions a spring motor. All of that tells us that inside here there must be a mainspring. And I know just a place where I can get one easily and for very little money. Obviously, this is a tape measure, and inside it there's a mainspring because when I pull out the tape, something magically pulls it back every time. Now, in order to get to the mainspring, we obviously have to disassemble the tape measure. This part, the measuring part, is I don't need that. Whoa! Okay, so here we can see a little locking mechanism. Now this is pretty thin, pretty sharp, so be kind of careful with it. There we go, finally. So it unlocks like this. We open it up, and inside is our mainspring. Yeah, I wanted to show you how it works, but now I kind of ruined it. It took forever, but I finally managed to wind the spring back. Now, this is the state in which it's in the factory before they install it into this part, which is the barrel. This is the natural state of the spring, this coiled state, and unfortunately in this state it's pretty useless because, as you can see, I can't wind it anymore. If I try to wind it, it just becomes a tighter coil. I can't use it to store energy anymore. If I try to unwind it, I can store some energy, but the more I unwind it, the more space it occupies, and that makes it useless too. Previously, when it was inside this barrel, it occupied always the same amount of space, and it was stuck inside the barrel. The spring never gets pulled out or in of the barrel. That's what this indentation here does. It gets trapped by this indentation. Let me show you. As you can see, it prevents it from being pulled in or out. But still, you can repeatedly store and release energy while the spring occupies always the same space. How is that possible? Well, it's possible because the spring wasn't wound into its natural state. It was wound like this, in the opposite direction, like this. So it was wound into its unnatural state, if you will, and the confines of this barrel prevented it from ever leaving the barrel, while at the same time it always wants to, I'm really afraid to release this now, it always wants to revert back to its natural state. So when you word it like this, it sounds like we're kind of cruel towards springs, but no, springs, mainsprings don't have feelings. We don't need a movement or a hashtag for them. Thank you very much. And while mainsprings don't have feelings, they definitely do have history. You see, mainsprings can be considered the first battery. Before we learned how to chemically store electrical energy, we learned how to mechanically store kinetic energy. Actually, no. Mainsprings are not the first batteries. The first battery is literally a rock that you take and raise it up. That's what we did first. Because when you raise a rock, you do some work, you create an input, and that input results in potential energy. And potential energy can be released. So what we did in the past is that we raised a rock, we tied a rope around the rock, and then we tied a rope to a mechanism. And as the rock was pulled back down towards the earth by gravity, we used that potential energy to operate our clocks. Of course, this was very inconvenient because it occupied a lot of space and you would have to raise the rock up again every now and then. Yeah. But then, fortunately, sometimes around the 15th century in Europe, somebody invented the mainspring. The mainspring allowed us to store more energy much more conveniently and in a much smaller space. Mainsprings revolutionized humanity because they allowed everyone to take time-keeping devices with them on the go. Mainsprings made pocket watches and wristwatches possible. But even mainsprings were kinda inconvenient all the way up to about the 1960s, because it took us centuries to figure out the right steel alloys and the right heat treating processes to give mainsprings the yield strength and the fatigue life that made it possible for them to be wound and unwound pretty much an infinite number of times. Something that we take for granted today, but up to about the 1960s, mainsprings were actually the main cause, the main reason for watch repair, because they simply didn't last nearly as long as they do today. Okay, so tape measure number 1 is a failure, and honestly, that's a good thing because it allowed me to get tape measure number 2. And this one is 10 meters, whereas the previous one was, where are the pieces? Whereas the previous one was only 3 meters. So this one can store a lot more energy. It's a bigger battery, and I'm going to need that if I want my fan to run as long as possible.
Okay, here comes the tricky part. This is already preloaded. Watch this. Okay, now we have to remove the tape again. Be free!
So here we have our barrel again, this time with a much wider and much longer mainspring, which means that we have a lot more potential energy stored here. And I've also learned my lesson. I'm not going to try to take this mainspring out of this barrel because it's probably going to just unravel into a ball of mess. Instead, I'm going to have ready another different main barrel, and then I'm going to try to somehow safely transfer the mainspring directly from this barrel to that barrel without winding or unwinding or any of that.
Okay, and here is the new housing for the mainspring, and now I'm going to transfer the mainspring from this one to the new one. And because this is kind of big, very sharp, I'm not sure what it can do, so it's better to be safe than sorry. I'm gonna get some gloves and some face protection too. Okay, this is a problem. As you can see, just a few coils are out. The rest is in, but that is enough for it to start escaping. And once it starts escaping, it's over. I will not catch it. I'm so happy I have gloves right now. Okay, I have almost everything in except this part. There's no other way. That's what I'm doing. I'm going to cut a bit. Okay, it is in. It is finally fully in. I have captured a mainspring. And as you can see, it is totally secure. Now, with this tab here, it cannot go out or in. But just to be extra sure, yeah, I took off the gloves. What an idiot. Just to be super extra sure, I'm gonna do this too. And so this part doesn't stay like this. I want it flat and non-dangerous. Done and done. Our power source is ready. Now let's design the rest of it.
Okay, so here we have almost all the parts already out of the printer. The only thing that's missing is the fan itself. That's being printed right now as we speak. I have already pressed most of the bearings, as you can see here. There's just one bearing missing, left to be pressed in. And done. Now, here we have the gears. As you can see, we have two gears fused into one. You have probably seen this anatomy on toys, clocks, you name it, many things. It is useful because it allows us to achieve a relatively high gear ratio while keeping the entire system pretty compact. Now, the whole gear train is supposed to go together like this. Okay, so we store the energy in the spring, and as the spring releases, it rotates and rotates the entire gear train. We have a 1:16 gear ratio, meaning that just one rotation of the spring barrel is going to achieve 16 rotations of this top shaft here, where the fan will be attached. But there's more to it than that, because I also tried to make the gear train efficient. And that's because every one of these fused gears is an opportunity. It's an opportunity because these two gears are just joined together. They don't mesh. And that means that we can change the gear specs from one to the other gear on the gear pair. So what I did is that I decreased the gear module going from bottom to top. The gear module is simply the tooth size of metric gears. Larger teeth are obviously stronger and as such have higher load-bearing capacity, but are also noisier and less smooth, which makes them better suited to low RPM and high torque. On the other hand, smaller gear teeth obviously have a lower load-bearing capacity, but are smoother, quieter, and more efficient at high RPM, which aligns perfectly with our application because we are increasing speed or RPM as we go up in the gear train, while at the same time decreasing torque. I have also changed the pressure angle for the last gear pair at the very top, which will operate at highest RPM. A 14.5 degree pressure angle is smoother, quieter, and overall better suited and more efficient at high RPM. It has poor shock resistance and is easier to strip with high torque, but we don't really have any shocks or high torque by the time the torque is transferred from the bottom to the top of the gear train. But all of my gear spec cleverness is going to be an absolutely useless drop in the ocean compared to the losses created by the imperfections of 3D printing. You see, when you print a gear like this, so two gears fused together and then together with the shaft, all as one unit, the top surface is always going to be pretty and smooth and almost perfect, whereas the bottom surface is going to be much rougher and uglier, and that's because it interfaces with the supports necessary. These supports are a consequence of the shaft. So the correct approach, which I haven't taken due to laziness, would have been to print the gear and the shaft separately and then just print a keyway in the gear, create a keyway, which I haven't done. Which means that now I'm going to have to sand all these undersides of the gears because I can already hear them, and you will now be able to hear them too. The high spots of all the rough parts are touching each other, grinding against each other, and of course, that's a massive efficiency loss. And we don't want that because this whole device is an exercise in preserving energy. The energy created by the spring, we want to preserve as much of it as possible, to transfer as much of it as possible to the fan. Everything we lose on the way means less rotation of the fan, and we don't want that, so now it's time to sand. I have good news and I have bad news. The bad news is that this doesn't work. It's a complete failure. The good news is that I know exactly why it's a complete failure and I can fix it. The problem is that I took the completely wrong approach when it comes to making this. And that's because I tried to make this whole contraption as rigid as possible. As you can see, I made even these brackets to secure it. It has bolt holes right here to bolt it down to some sort of like a wooden plank or something. And that's because I thought that every kind of movement, every kind of wiggle, every kind of imperfection in the rigidity of the device is a loss. The number one problem that this approach caused is that trying to print giant high infill pieces like these brackets, let me take everything apart, it leads to imperfections. Trying to print something as big as this with 35% infill and 4 walls, on top of this, the whole thing all of this was on supports, and such a heavy part as it prints, it warps. So it warped. And when it warps, the alignment of the gears with each other becomes incorrect. And so instead of being perfectly spaced, because they're individual holes for the bearings determine the spacing of the gears, but when you warp the whole parts, these holes move, and now the gears are pressing hard against each other. They don't have the right space, they can't breathe, and so it's impossible to turn them. The only method I could use to successfully get this to rotate was to actually separate the housings, to get rid of these brackets, and to give it some breathing room. The other problem I have is that this shaft on my main barrel for the mainspring broke. The shaft broke, but I fixed it by printing another hollow shaft and bolting it into this. But obviously now this isn't perfectly in the center because the hole that I drilled in, it's manually, I got it as close as I could, but now this has a bit of up and down motion, but I really don't want to print a different barrel because then I would have to transfer this to another barrel and I do not want to do that again. But I think this is good enough, and I can use it if I give the whole system some more breathing room. I was trying to imitate clockwork. I was trying to imitate metal precision with plastic. And that's because I was too overconfident, thinking that, hey, I have access to technologies from the present, and so I can beat manufacturing from the 1900s. That's not true. Metal is still metal. Precision clockwork is still precision clockwork. Even if 100 years old, I cannot just, take it lightly and, look at it from some high chair or whatever. Now I have to get back to basics. This has to be designed completely differently with the limitations and the possibilities of 3D printing in mind. Okay, so here is version 2.0. As you can see, it's dramatically more simple, more sleek, more elegant, a lot less filament. Now it even has a bit of give in it to accommodate all the imperfections. The gears are no longer together with the shaft. Now they are using this Lego knockoff axle system. And they also can play a bit on it. So now we are actually loading the fibers. We are not trying to rip the shaft off. We are not loading them where they adhere to each other. We're not attacking them where they're weak. Instead, we are trying to do this to the fibers, and that's impossible because this is where they're strong. We're going in favor of their strength. However, once again, I have good news and bad news. The bad news is that this broken shaft on the original barrel is simply too inaccurate. No matter how much I try to accurately drill it in the center and screw it into the center, human eyes and hands are not precision instruments, and there is always a bit of out of round, a bit of play. And so when I try to install it into the new housings and I turn it around, I don't know if you're gonna see it immediately. As you can see, observe, there's simply far too much play. The whole thing is wobbling around more than I can afford. The good news is that I'm having fun now. I'm solving a completely different problem, and the problem that I want to solve now is how do we save this? How do I save this barrel? How do I attach a shaft to it once again? How do I give it a shaft while keeping accuracy? How do I put it in the dead center while still keeping this part that I need so much? And I think I have an idea. So what I have printed is this gear, which is exactly the same as this gear. And then I have printed this alignment sleeve. So the alignment sleeve goes onto this gear. As you can see, it's a pretty tight fit. In this gear here, we have this hole for the axle. We're gonna put this in. Again, there's gonna be a bit of play. And again, we are loading the fibers in this direction. This is printed, the layers are like this, and we are loading like this, which means that this is virtually unbreakable under normal conditions. And now we put it all together in the alignment sleeve. And this sleeve guarantees that these two gears are now perfectly aligned. And as you can see, I have these 4 holes prepared. And voila, we have restored a shaft with a bit of give too. And as you can see, the gears align perfectly. Okay, here it is in all of its absolute ugliness. But I'm finally ready to try it, and I've already tested it a bit. It kind of works. So, obviously, the most important thing here is not just whether it works and whether it, creates a breeze, but the ratio. The most important thing is the ratio between how much time you spend winding and how much breeze you get out of your fan. So here I have my stopwatch ready. I'm going to start it, I'm going to wind it, and I'm going to release it, and then we're going to see what happens. Okay, that's enough. No overkill this time. That took 39 seconds. I can wind it a bit faster. Now when it gets to 45, I'm gonna let it go. Two minutes and 30 seconds. So for 40 seconds of winding, we got 1 minute. So for 40 seconds of winding, we got 1 minute and 45 seconds of breeze. Extremely light breeze. I have this here. Let's see, what do we get? We're getting like 0.3 meters per second, which is fast. This was like 2 days worth of research and development. And I think it has potential. Like with more effort, with more precision, with just better everything. I think I've also figured out why nobody's making this. Because it will be expensive. It will be really expensive. And you would need to use it for a lifetime, maybe even more, to make it pay for itself in the tiny little energy savings that it would create. It would be expensive because this is genuinely precision machinery. The only way I could get it to run is to keep it all loosey-goosey and let it just, work itself into whatever shape it wants. Because every little imperfection, every little inaccuracy, doesn't matter how small, it all stacks up. And everything has to be dead accurate. It really is, it's a good name for it. It really is a clockwork fan. This also makes you realize just how incredibly impressive the craftsmanship of the early 1900s was. Think about it, no CAD software, no CNC machines, none of that. And they still got it running 15 minutes, maybe even 30 minutes. That requires, I'm sure of it, extreme accuracy, extreme precision of manufacturing, fully understanding the system, making no mistakes anywhere. Achieving that back then, wow, maybe we haven't come such a long way. I'm pretty sure those things were really expensive back in the day, probably maybe even the cutting edge of technology, probably only the very rich colonialists or whoever could afford it back then, who knows. But still, the people who made them, yeah, impressive. And they would still be expensive today. They would still really be expensive today. That's why they're not everywhere online. yeah, thanks all for watching, and I'll be seeing you soon with more fun and useful stuff on the D4A channel.